This material has been reproduced and communicated to you by or on behalf of the Australian National University, in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you must be consistent with the provisions of the Act. Do not reproduce this material. Do not remove this notice.
Why are we going to be covering what we're covering? All right, if you think about this wonderful phrase, physics is where the action is, that's come from the book Z, Group Theory in a Nutshell. The action, as I'm sure you all know, is this path integral of the Lagrangian. Okay, and our principle of least action is just that the physical solutions are the ones that extremise this function. So if we vary a path slightly and to first order the change in the action is 0, then we consider that path to be our physical solution. Yeah. And from this principle we derive the Euler-Lagrange equations, which in standard classical mechanics are equivalent to Newton's equations of motion, right? Okay, so obviously some advanced calculus is going to be useful here, yeah? And then the other part of the course is going to be based on group theory. So group theory is language of symmetry, and as you all know, I'm sure, it is the symmetries of space that imply conservation laws. So if you're, so the very fundamental, or the first and simplest example of that is, I guess, Newton's equations for gravitation and the way planets move within a gravitational field. That gravitational field is spherically symmetric, yeah? So that means the potential energy only depends on radius, the radial distance. And then if we know that the entire Lagrange equation has to be invariant with respect to those spherical symmetries, it tells us that absolutely the only terms in our equation that can be present are those that depend on the magnitudes of our vectors, okay? And so it's truly this principle of symmetry that immediately restricts what our equation can look like, right? So the potential energy only depends on position squared, and the kinetic energy only depends on the speed, the velocity squared, okay? And this seems quite trivial, right? Because it's so ingrained in your knowledge of physics, this sort of thing. But the same types of arguments can be applied more generally. So maybe your system only has a discrete set of symmetries. For example, if we're trying to find atomic orbitals in a molecule, okay? The symmetries won't be spherical, they'll have some other symmetry group, but the presence of those symmetries will have major implications for the form of the Lagrangian and also the types of solutions that are possible. Okay. Yeah. So I like to call this course, my nickname for this course is Calculus and Linear Algebra on Steroids, because we're basically taking, your first year, I guess most of your physics tools are based on that, undergraduate maths training in calculus and linear algebra, and we're just going to take them to the next level in this course, okay? So why linear algebra? It's because group theory is really a generalization of the way we